Good afternoon, everyone. It is 3 p.m. in the Netherlands. We are all around the world today, so I would like to start with a message from my side. No matter where you are, wear a mask. No matter where you are, wash your hands. We all want to enjoy Christmas and we want to start traveling again as soon as possible, hopefully in April or May. Welcome to another edition of the Epic Online Technology Meetings. Wow, the numbers in the Epic meeting on Monday, December 14th are going to blow your mind. Imagine if using plasma at 30,000 degrees C is part of your daily routine. You wake up in the morning and today you had to build a 360 meters cruise ship made of steel with up to 40% less material and 40% less energy. And that's where photonics comes in. Modern shipyards need laser hybrid welding processes to join vast steel panels. Heat has always been crucial in building steel constructions. Laser processes result in highly controlled metal melts to precisely fill the seam. The aircraft industry has two additional requirements: lightweight and aerodynamics. Manufacturing processes are expected to result in rivet-free surfaces. In addition, carbon fiber, thermoplastics, and new materials have to be manipulated with zero waste. And in a world of leased aircraft and marketing campaigns, quick painting and especially deep painting has to be faster and cheaper. So what will the shipyard and aircraft hangar of tomorrow look like? What are the challenges in making the next generation high-power CO2 and fiber lasers? What shape is needed for the optical beam in processes involving such high power? On December 14th, we'll examine the next steps for shipyards and aircraft manufacturers and how high-power lasers and their supply chain are key to this competitive industry. My VIP list includes laser industry leaders like Trumpf, Laserline, Precitech, George Fisher, Siemens, Prima, Lumentum, SPI, and their current and dream partners such as Fincantieri, Avio Aero, Safran, and ArcelorMittal. And to make the innovation happen, we need the research powerhouses like Fraunhofer, AEMen, Lasercentrum, and Hilase. Join users and suppliers in our Zoom room at exactly 3 p.m. on Monday, December 14th, or follow the fireworks in YouTube. Lasers at this scale are truly awesome! Wow! Thank you very much for this fantastic campaign which I've built in the online technology meetings. We keep really getting lots of requests to participate. We keep growing. Epic is now 660 members. We keep getting lots of feedback from how to improve this. And I have to tell you, we are only 2 episodes away from the very well-deserved Christmas holidays. Next Wednesday, we have Photonics for the food and beverage industry, and it's shaping up to be excellent. But I would like to remind you that we already announced the topics for the Q1, and we already have topics there for high-power, ultra-fast lasers, for augmented reality, for co-packaged optics, for the oil and gas industry, even green energy. So I would like for all of you to have a look at them, and if you see that this topic is in any way relevant to your industry, register online, or also send us an email and tell us how it's relevant so we can position you in the supply chain. Thank you very much for making the epic dream possible. I'm here just talking on behalf of a group of friends. We are 14 people, half of them with a PhD, knowing the technology very well, but also people who are also experts in the marketing side, people who are experts in the raising capital. Our idea is that we can support the photonic industry by organizing events, provide access to the network, raising investment capital from seed to large capital investment. We have the biggest website to find a job in photonics, www.jobsinphotonics.com, and we also provide to all our members for free market reports. We are that nice. We buy market reports from Thematis, from Joel, from Strategies Unlimited. We give all of these reports for free for our members. But that's all from Epic. Today we talk about the industrial laser manufacturing for the naval and aeronautic industries. I would like to first of all acknowledge our media partner, AZOnetwork. Thank you very much for the strong promotion and for the communication and the great feedback that you're providing us for these online technology meetings. Thank you, AZOnetwork. And today, this meeting would be possible with the support of our sponsors. Let's go first to Israel, Civan. Civan, you're looking for a single mode high power laser or a dynamic beam shaping 16 kilowatt plus, Civan is the right company for you. But if you're looking for IBS coatings, ion beam sputtering coatings for high fluence optics, even in the ultra fast region, OPTOMAN is the best partner for IBS coatings in optics and laser optics. And if what you're looking is a back-end packaging processing, or you're looking for wire bonding, you're looking for a partner to help you, to support you with the automation, packaging, assembly, AEMtec is the right partner for you. These are our sponsors today, but perhaps the most important person in the meeting today is my co-chair and very good friend, Francesca Moglia. What's in the menu today?
Thanks a lot, Jose, for the introduction. Thanks everybody for being here on YouTube and in the room. But now you know, this is the list. It's a bit a boring slide that we have here. This is the one of the speakers, but that's what is showing exactly what is in the room now, or that actually sign up for this meeting. So it's really a pleasure for me to have here these two applications that are really important also for laser in the industrial laser world. So we have today, we are talking about aeronautics and naval mainly. So we will see if there will be room for automotive as well. So there is interest also from this side, and we will find also the overlaps, differences, so that all the industrial laser manufacturers that you see here in the middle, the industrial laser system integrators, of course, are making a big part of this meeting. But let's not forget about the future industrial application based on laser that are made by our R&D teams. That is here on the, you will see it on a bit on the left in the center. And then, of course, let's not forget about our full supply chain. So optics, optical system and solution, testing, also sensing systems. We have also the standard and OEM machine builders that integrate lasers, but not only. So we will see what is the offer there and the alternatives to compare to lasers. And then the services. Of course, we have many of them. It's really a pleasure for me to introduce also Pulsate, that is really serving the industry of the future SMEs that are not very familiar with laser yet, but we can teach you. So now it's time to give you back the word to Jose, and let's go and meet maybe at least a few of you here in the room, hopefully many.
Not so fast, Francesca. I would like to acknowledge and thank you for the great effort, which means to build this supply chain. You put a lot of hours and passion on having the end users and the R&D partners and all the way to all the needs for cooperation. This is a lot of work. Thank you very much for what you have done. I would like to remind everyone that this slide only represents the companies who register for the meeting today. So if you're an EPIC member and you missed your logo in this slide, that only means you did not register. We never forget any of the members. And today, as all of you know, we are live in YouTube. So many hours, more than 300 hours of streaming in YouTube already. Thank you very much for all the people who are following YouTube. Thank you very much for posting your questions. Please post your comments in the chat. If you want to get in touch with any of the participants, all you have to do is send me an email, jose.pozo@epic-azo.com. And if you have any question and you put it in the chat on YouTube, I will be reading it in the room. And this is also valid for the people in the Zoom room. If you want to get in touch with each other, you can always send me an email after the meeting. I will make the introduction. But you should know that after the meeting, at 5 o'clock, because we'll finish on time, at 5 o'clock, you can stay in the room, and my colleague Rena Jelinkova is going to set up one-on-one meetings in private rooms for you to participate, for you to talk to each other, and for you to make sure that you can do the business that this topic deserves. Thank you very much, all of you. Let's start with the business. Let's start making the right thing. And we wanted the company who has set up the supply chain for high power lasers in EPIC to take over and to be the first speaker today. Prima Power, all the way from Italy. Mohammed, Naeem, thank you very much for being with us. Tell us about Prima Power. Tell us about their position in the supply chain. And most important, it's an EPIC meeting. So tell us what you can do for 651 members and what 651 members can do for Prima Power. The floor is yours.
Thank you very much.
So all we have to do now is to share the screen. So at the bottom of the Zoom room, you have the green arrow up. Yes.
Okay.
Perfect. The floor is yours.
Right, good afternoon, everybody. Thanks for giving me the time to present this presentation. So I'm going to talk about laser material processing in aero engine industry. So only got 6 minutes, so I better start going. So basically, I just want to introduce Prima Power Laser Dome. We're based in USA, in Minnesota, and we make a 3D axis system for mainly aerospace. We also do for medical, automotive, and electronics. For my mainly talk is going to be on aerospace. So I think aerospace, there are a lot of application of laser processing in aerospace, mainly drilling, cutting, welding, and this presentation will highlight some of the examples using lasers when you manufacturing aero engine materials. So as you know, laser drilling has been around many years, and that's the #1 application right now in aerospace market. Laser drilling is using lasers. In the past, people used to do Nd:YAG lasers, but now recently, last few years, they've been using QCW fiber lasers. And the reason the people use laser drilling to drill this very difficult material, these are all nickel-based alloys, which are extremely difficult to drill conventional drilling. So they end up using lasers. The advantage of laser drilling is that it's very quick, it's repeatability, and you can drill at different angles. And some of the materials are very difficult to drill traditionally. But if you look at the hole drilling, these are some of the components. So if you look at blade, vane, afterburner, these are typical diameters. You tend to drill 0.3 to 0.5, and then typical thicknesses. And there's a number of holes, anything from a few hundred up to 40,000 holes are drilled currently using lasers. So laser drilling, basically you can drill in different methods. So one is trepanning, where you actually cut the hole out. And there's a percussion drilling, which you do a single shot, which is very quick. So the difference between trepanning and percussion is very quick in terms of timing. So if you got 40,000 holes to drill, it will take a long time to actually trepan it. So people tend to percussion it. And trepanning, you tend to get very good quality in terms of the taper and the recast layer. So these are some of the micrographs. If you look at this one, this is most of the material used in aerospace are TBC coated materials. So i.e. to increase the engine life. So it's coated with TBC, which is extremely difficult to drill. Because TBC tend to crack, so you need to make sure you develop the parameter where you actually drill through the TBC and into the pair material. So this is a good example. So most of the holes are actually done at an angle. It's very rare you drill at 90 degrees, so most of it 30 degrees from the surface. So this is an example of drilling to a TBC. So if you look at the top, this is through the top of the hole, and this is a cross section. And when you're drilling hole, the one thing you need to look for, there's no cracking in the pair material, and there's no cracking in the recast. So recast is the material which is solidified along the length of the hole. So this is example of TBC. This is another example of trepanning holes, very small holes, very closely spaced. Again, it's a challenge. And again, if you look at it, this is Astro X, 20 degrees to the surface. Typical diameter is 0.2 millimeter diameter. But if you look at the aspect ratio, which is 47:1, so it's, the actual hole depth is around 10 millimeters. This is percussion in a uncoated Hasselhoff X, which is 30 degrees to the surface. Again, you can see the top of the hole very round. And this is a cross section against very little taper from top to bottom. So again, that's another example. Typical diameter is 0.5 to 0.7. And there are also some application where you actually drill very deep holes. So this is example of 10 millimeter thick in Vassalloy, which is 30 degrees from the surface. So actual depth of the hole is about 20 millimeters. So the thing to point out here is actually the how parallel the hole is top to bottom, very little taper, very little recast layer. So these are some of the examples from TBC to very thick using currently laser drilling being used in aerospace. Other application which is gaining a lot of interest in laser welding. Currently people tend to use a lot of electron beam welding on conventional, which is TIG or MIG. But since the fiber lasers coming in the market and with the high power, more and more people are switching into the fiber laser welding. The typical requirement in laser welding of aerospace material is not the cycle time is important, but the most important thing is the quality. So these are some of the things I highlighted. No porosity, no cracking. The weld width have to be certain dimension, top and bottom wing to give the strength. And most of these materials are either Inconel or titanium, so the gas shielding or making the weld without any oxidation is very important. So some of the examples, again, some unfortunately, when you're working for aerospace people, you cannot share most of the information, it's confidential, so I can just highlight the generic data. So this is an alloy 3.2 millimeter butt joint. Again, you can see very nice, well, no porosity cracking. Haynes 230, Incona 718. And also there's some requirement welding this material using a filler material, because some of the requirement, the fit up is not so good, or there's a metallurgical requirements, we end up using filler. So this is a Incona 625 using Incona 625 wire, so that you can see beautiful top beat and bottom in the undercut. And this is a T-joint, again using a filler material. So there are requirements using filler in welding of aerospace material. Laser cutting is another application where a lot of 2 and 3D cutting been done. This is an example of a blade profile been cut in 5 millimeter thick for land bed turbine. This is Hasbro X using oxygen, again, very good repeatability and very small dimension. Other thing which is gaining a lot of interest is actually composite material, which is a plastic composite or metal matrix composite. So this is one example of the video, which is a metal matrix composite. The whole diameter, whole depth is about 35 millimeter deep. And this is actually percussion drilling. And you can see it's taken about 10 seconds to drill for the hole. The actual depth of the hole is about 35 millimeters, which is about 1.38 inches. So for this one, you can't actually cross section, and so we actually measure the hole taper using a pin gauge. So this is about 35 millimeter deep, and now we're going to put a pin gauge through to make sure the hole is quite parallel. So these are some of the things which are currently doing composites. And the outlook, especially in aerospace and also space engineering, is very promising. A lot of interest been generated looking at dissimilar materials. So that's welding are the new alloys. So basically welding a different grade of Inconel, stainless steel to Inconel. Also a lot of interest in aluminum lithium alloys, which is again for space engineering, spacecraft, the weight is very important. Polymer matrix composites again is cutting, drilling, and also surface modification. And the biggest interest right now is a metal matrix composite, where we're looking at different silicon carbides, aluminum boron, nitride carbide, and these are very difficult to actually drill, so we're doing a lot of work on it. Another thing I did not mention, which is quite big in aerospace, is additive stuff, so that's a separate topic altogether. So that was just a brief introduction of what the laser are currently be doing in the aerospace market, especially for aero engine materials.
Thank you very much, Mohammed. Thanks a lot. Thanks a lot for this nice overview. So now you're maybe not familiar with this, but I will just make you the epic question. That is the one that then everybody else also will hear and they will be prepared for. That is, what can you do for them, the audience, and what can they do for you? So the audience and the 650 plus people, as Jose already pointed, exactly. We are a bit here, but we have a potential.
Okay.
So Mohammed, what are your interests in being in this meeting today? So you see there are some end users, there are some integrators, some laser experts like you. So what is the room for collaboration here?
Well, basically when you're working with aerospace material, it's very difficult to actually buy this material off the shelf. So it'd be nice to work with end users who can actually give us the right sort of materials to make sure that whatever R&D work we're doing a laser done, actually it is useful to the aerospace people. So like when I was talking the last slide, I show you actually drilling the metal matrix composite. It's very, very difficult to get this material. So it'd be nice to have end users who make these materials to work with them and see what the laser can do with that material.
Very good. So you're offering really directly, please end user come. So I'm repeating this. Contact Mohammed or us, and then we will put you in contact with Mohammed. So composite materials, we saw you have a long list of also combination and expertise. Yeah. And also you said there are some issues that for sure the end users are aware of. So if someone of those end users in the room would like to comment on this, otherwise, guys, I know, you know, we pick you. We are not leaving shy people silent. So I don't see any hand yet. So I see that, for example, I know I have Jose has a hand.
I have always my hand up. This is what I always do at the school, and the teachers never like me. We have a problem, which is that, well, we have a huge solution, which is we have great optics for multi-beam solutions. We have developed this with companies like Holo, or Francesca will tell you maybe later about the LAMPAS project. We are extremely excited about this. In the technology you're presenting, especially where you're doing the multi-spots, that was really one of the highlights of your presentation. Is there a room, in your opinion, to try to test, to work with companies who are splitting beams at high power and making these multi-beam patterns?
Yeah, definitely, because I think multi-beam, especially when we're doing some, basically, as I pointed out one of the slides, the people in aerospace tend to use, especially the fit-up is very bad when it comes to laser welding. So the only solution is to use filler material. But the problem with the filler material is it creates very complicated setup. The cost of the system goes up. It'd be nice to have actually various, like a twin spot or multi-spots where you actually can bridge the gap without actually adding the filler material. So like we used to do in automotive when you're doing a tailor blank welding, we used to have like a twin spot technology where you actually bridge the gap, different gaps. So the multi-spots will be very useful for these sort of application.
Is there a challenge for getting these multi-beam solutions when it comes to the high power that you need? Is there something that you have been experimenting? What is the current state of the art?
Well, current situation is we are experimenting with different, multi-beams. As I say, unfortunately, it's very difficult to share some of the information because it was confidential. So we are actually looking at these up to about 2 to 3 kilowatt in terms of average power. So when you mention average power, that's what we're currently working with. And this is mainly used for actually laser welding application we're doing.
Very good. So if anybody in the EPIC network has a solution for multi-beam, for very high power, for very high fluence, it would be nice to make an introduction. I will do so. Mohammed, thank you. And back to Francesca.
Thanks a lot, Jose. Thanks a lot also to Mohammed. So Mohammed, you mentioned at the end of your slide that there is the additive manufacturing world also, but is a big parenthesis that you couldn't have the time to discuss, right? But what is actually, can you maybe a bit introduce this to what is the expertise of Prima? Well, additive, actually, your colleagues, or maybe you as well. So this would be nice to know. Thank you.
Yeah, we especially for additive stuff we're doing in US, where there's a lot of requirement to actually repair the tip of the blade in turbine blades. So we're doing a lot of work on using additive to repair that. So the problem with additive, especially repairing blade, is you need to make sure that the metallurgical compatibility between the powder you're using and the blade you're repairing is exactly the same. So we're doing spending a lot of time understanding the material side of the additive stuff. Our sister company in Italy, they're doing a lot of additive stuff. They develop the system and doing a lot of basic R&D work for all the industry, not just aerospace.
Very good. Thank you. Then last word before we go on to Tiffany, that she put courageously in the message in the chat. So maybe Tiffany, you can introduce yourself briefly and say what Skylabs can do, not only for Mohammed. Thank you.
Yes, for sure. Thank you for the introduction. At Skylabs, we do beam shaping for high power application. We have made trials with up to 16 kilowatt solutions, either for multiple beam shaping. We have solution for donut shaping, any asymmetrical shape and things like that with very good depth of focus. So it would be really a pleasure to be able to discuss a little bit more about your needs and about our solution and to see how that could come together either with you and with also other suppliers for such solutions.
Yeah.
Thank you very much. So Mohammed, you have already one bullet point in your list.
Okay, thank you.
So now we maybe go back to our agenda. I see loud and clear that is maybe we can test also your microphone. Christophe from Thales is there. Welcome. You can unmute yourself.
Okay.
Yes, now I hear you. Welcome. And we are really looking forward to your talk. So please, the floor is yours. Thales and the laser expert from Thales. So
just let me try to share my slides.
Yeah, the green button below.
Yeah, just now I have to.
You see the green button?
I did not try before.
Now you confess your sins. You shouldn't confess your sins so much. So if you try a bit, otherwise I can share it for you. If you give up, I do it. So let me see. So let's go to
Christophe Simon is the product line manager of Thales LAS. There we are talking about the key company in the value chain for aircraft manufacturing. We're all looking forward to helping you with your challenges. I'm really looking forward to this presentation.
I'm sorry for the...
Never apologize to us. The presentation is already up. We'll show it from our side. The floor is yours.
Are you seeing the screen now?
Yes, we see the slides. We are sharing them from our side. All you have to do is present away.
Okay, it's Francesca. Okay,
Yep.
Sorry. Sorry, I am using a private computer and I did not try before.
no problem.
So yes, I am Christophe Simon-Boisson. I am a product line manager for scientific industrial lasers. So I have 5 slides. So maybe let's go to the next. Yeah, so briefly, just to say where we are involved. And so we are involved in basically 3 areas. The science, where we are mostly now with very big projects that sorry, the picture are quite small, but you see, for example, we have been the first to be successful to deliver 10 petawatts for high peak power lasers for science. Industry, we are talking about after, but also space. Right now we have a laser on Mars since 8 years, and it will be joined next year by another one, which is right now in the space. So I don't say more. I prefer to go to the next. Okay, so today my talk is about laser shock pinning. So laser shock pinning is I have chosen that because of this is a process which can be applied successfully to both aeronautical and naval field. It has been, to be honest, really developed thanks to the support of the aircraft industry and particularly in the US. But recently there are some companies which have been also published about use for naval applications. So this process is basically, sorry for the French words in the scheme, but basically the idea is to use a high energy short pulse lasers, very short pulse. We talk about nanosecond pulses. So the idea is to send the pulse to a metal part. With the high peak power, you are going to vaporize some material and to create a plasma. You have to confine this plasma in order to have a maximum effect, to optimize your effect, and it will generate a shock wave into the material. And this is this shock wave which is important because this shock wave will create constraints in the material. It means it will be compression constraint, and these compression constraints are very useful for the lifetime of such parts. So that typically the order, so the pressure coming with the shockwave is quite high. We talk about gigapascal, and the laser typical energy is joule or fraction of joule up to 10 joule of 10 joule. That could be essentially right now in the state of the art is mostly in near infrared 1064 or 1053. Its pulse range is typically between 5 to 15 nanoseconds, and spot size is typically 3 to 5 millimeters, could be more, but basically you are generating an intensity on the place to process that which is several gigawatt per square centimeter. So there are some applications from the same family. So of course, laser shock pinning is the the most known, but you have also the what we call LASAT or LBI, which is the laser shock adhesion test or laser burn inspection. So that's mostly used for composites. It's more recent, that laser shock peening, and it's essentially a non-destructive evaluation technique, not really an eye of the part. You have also laser stripping and many variants for in the field of material characterization. So what Thales is doing in this field? So Thales is doing different things. So we have currently a joint PhD work with a laboratory in French, which is the ENSAM Paris, the PIM laboratory. So this work is essentially to optimize the laser parameters. So the work is on the LSP process, but the purpose is to optimize the laser parameters to have the best and the best quality and the best speed process. We are also involved in 3 collaborative projects at the French level. So that's one what called Monarch, Forge Laser, and Transfuge. So these projects are made with consortiums which involve the research, the technology providers as we are, but also a lot of end users. So we have Airbus in the 3, we have Safran in two of them. We have in Transfuge, we have also different industrial companies, not only aerospace. We have Naval Group from France. We have representative for car industry. So it's really multidisciplinary consortiums. And last but not least, we have already in the portfolio, and we are also continuing to develop some laser products we think which are suited for LSP. So maybe going to the next slide. So to give you an example of the what the real effect is, for example, you can see the 2 pictures on the right. You see the picture which is in the right, quite in the middle. You see what happens if there is a crack for example, a corrosion crack initiating and propagating within the material. And you see on the extreme right, on far right, you see what happens if you have applied the laser shock peening process. So you see that then you can avoid or limit the propagation of the crack. So that's the reason why this process has become quite popular for aircraft industries, because they really want, by using this process, they want to increase the fatigue life of parts, so that they make the maintenance less frequent and less expensive, because they don't have to change the parts if there are too much damage. So there are real economic stakes on that. So maybe we can go to the next. Okay, so in this slide, I have summarized the latest results of this PhD work I was talking about. We are doing in the collaboration with the PIM lab at ENSAM Paris. And this work, the student is Alexandre and Pierre. So he did some publication. I think for those we are interested, there is a reference at the bottom of the slide. So the idea was to study the results of laser peening as a function of laser spot size. So what the setup is, you send a laser pulse on the metal target. You have a confinement layer, which is essentially water. So most of the time up to now, it's water. You shot a laser pulse and you generate shock waves. And so you monitor these shock waves, and in particular the velocity. You can measure the velocity of the shock wave by using a device which is called VISAR. So it's an interferometric device which can deliver the velocity of the shock wave. And we were also recording the radiant intensity with a photodiode. So what the curve you see on the right is the velocity of the shock wave as a function of time for 3 different diameters of the laser spot. So the in red is 3 millimeter, in blue is 1 millimeter, and in gray it's 0.5 millimeter. And what we see is that the rising part, which is generated by the laser pulse, is quite independent of the spot size, but the release, the falling part, is very, very different between the 3 situations. So they are, and the falling part is much faster if there is a small spot size. And the consequence is that with such behavior, you reduce the thermal loading of the material. So you are able maybe to even increase again the fatigue lifetime of the part you have processed. So let's go to the next slide. I think that the final slide. Yeah, so the final slide is just to show what is the solutions we have at Thales for this laser shock pinning process. So we have typically 2 categories of lasers: the flash lamp pump lasers and diode pump lasers, so all solid state lasers. And you see that so what you see what you see as the parameter energy is the energy in the green, because they are often used in the green. And typically all of the flash lamp pump laser can be used. And also in the diode pump laser, we can use essentially the TEIA, which is laser delivering. You have details below, up to 1 joule at 1064 and 700 millijoule in the green, at up to 200 Hertz. So what is interesting in that solution is that this new laser, which is a relatively new product, it's perfectly fitting with the findings of I have shown in the slide before, because if it's better to work with a small spot size, and you need much less energy per pulse. And much less energy per pulse means, for example, the kind of energy we may find we may have with the TEIA. We don't need, for example, this huge energy we have for example with Gaia and even Atlas even more, which is tens of joule, even up to 100 joule. So it means with 1 joule or even less, you can do a lot of things. And the other interesting thing, so then the first lesson is that you are performing a better quality laser shock pinning. The other interesting thing is this new generation of laser has a much larger average power, and the average power will determine the speed of the process. So it means the speed of the pinning process will also increase. So that's we find these solutions are will be very effective for laser pinning, and that's also a lesson.
Christophe, this is spectacular, really, really spectacular. You know, when Francesca told me that Thales was going to give one of the first presentations, honestly, I was thinking they're going to tell us about their position in the market and how important it is as a prime for aerospace. You told us about the LSP technology and the clear challenges. And Christophe, we have a lot of questions for you, really a lot of questions. There's huge room for cooperation. So let's start. I have the first question is from OPTOMAN. Giuseppe, how are you doing today? The floor is yours. What's your question?
Hi, Christophe. This is Giuseppe from OPTOMAN. No, my question was just related to the fact if you have ever have tried to use short pulse lasers to perform the laser shock peening. I read some articles and seems also this could be an evolution of the standard diode pump or let's say double rod lasers.
Sorry, what? Sorry, I did not catch your question.
Oh,
what is the
no,
question?
the question is that if you tried with a short pulse laser like picosecond or femtosecond lasers.
Ah, okay. Right now, the research group we are working with the most in Paris, they don't really think that lowering the laser pulse duration is so effective. But this is a very good question because, for example, there is one group in Japan which is trying to at Osaka trying to develop the process with the femtosecond lasers. To my knowledge, is only this group right now, but there might be also in the future. And of course, what we have to do in the very near future is to, for example, to work with still with nanosecond pulses, but maybe trying to reduce a little bit the pulse duration. What we are doing now, because it's also our next step now is to go also to have some very first process platform in Paris at this lab with a TEA and try to make some process optimization and potentially parametric studies as a function of pulse duration. But in the first time with a limited range that typically from, let's say, from 5 to 20 nanoseconds. Not
Christophe,
that big.
this is a bit like a Eurovision show. First we had Italy, where Giuseppe. Now we're gonna go to Israel. We're gonna go to Karen. Karen from Holo.org. What's on your mind?
Thank you for the introduction. I was wondering if you believe that the LSP process can be improved by using a flat top distribution of the laser beam.
Yeah, that's a great point. We on this platform we will have a DOE.
So ours, I hope.
I'm not sure. So to be honest, but yes, that's the idea. Is that and so we have recently characterized the beam profile, and maybe that's so this we think it will improve, but maybe we have to work on DOE design, maybe to produce even better beam profile, even better ideal flat top.
I think Karen could not dream of a better answer to your question. We have one more question in the room. We go now from Israel. We go to Eindhoven Rock City in the Netherlands. Harry, what's on your mind? Let me unmute you. Yes, we need to unmute. Yes.
Yes, I'm here. Okay, very good. So as a powder bed laser fusion equipment supplier, we also know that materials printed in this process are prone to micro cracks in the surface. So usually we do mechanical shock peening, but I was also quite curious. Is there already an experience with using this technology LSP of eliminating this effect, and actually then bringing those parts into especially the fatigue properties of those parts into acceptable regions? So is there any experience yet, and is it something maybe we could share or could connect to?
You mean in additive manufacturing?
Yes.
Oh, that's a great question. So we used to have to sell a laser to a group in Lausanne in EPFL working on the subject. Mm-hmm. So we don't have very recent news from them, but I could share later the name of the group and some people working them, and from other parts I heard that there could be some interest raised on combining some LSP technique to the additive manufacturing stations. Yeah.
Yes. That's at least we also use lasers, but they are continuous lasers and not pulse lasers, and that maybe but it could be a combination. But this is really a future outlook where we, could combine innovations and make a beautiful sum of new possibilities.
Christophe, what a way of starting the meeting, Harry, as well. What a way of starting the meeting. We already have a challenge on DOEs. Christophe, you don't know what you have done. We prepared too many introductions on this. But there was a company which I think there is a clear room for cooperation with Thales. And this company is Civan from Israel. The dynamic beam shaping that they can do is quite outstanding. Ami, do you see some room for cooperation with Thales, or do you have something to share with us?
Yes, thank you. First of all, always a pleasure to join your webinars. I'll give a short introduction for Civan just to give the context. So what we do is we develop high power fiber lasers based on Korean beam combining. So we can offer single mode CW lasers up to 100 kilowatts. And just to explain, so what we do is by controlling the relative phase, we can control the location of the beam. So the one main advantage is having a single mode laser and having a small diffraction is that we can have remote operation. So this is very useful for welding in aerospace and aeronautic applications. And the second thing and the most interesting is the ability to have the dynamic beam, which is basically unlimited beam shaping and beam steering. So just one example of how this can be used in drilling applications. When drilling in a material that is coated, you can adjust the power distribution for each layer and just very quickly switch between the different beam shapes. So I think that what we, Civan, can offer is because we have the ability to design in just a few minutes almost any arbitrary shape, is to offer to test in our applications lab any crazy beam shape that someone wants to try. And what we are always looking for is challenging whatever application that can use beam shapes or different power distribution that cannot be solved at the moment. We are always looking for new challenges to try in our applications lab.
Thank you very much, Ami. What kind of cooperation would you like to do with Christophe? This meeting is about cooperations. I will say that.
Yes. That's a good.
I love putting people on the spot, asking this, what can you do for him?
Yes. So I think it comes back to what I said. I think we are always looking for ideas for different beam shapes that can help different processes and discuss different designing new beam shapes that can support this different process.
So why don't we continue the Eurovision tour? And now, wait, Ami, because there's a question for you. Tim from Fraunhofer IAPT, what's on your mind?
Yeah, hello, also from my side. I have a question to Civan about the beam shaping equipment. How much is the spot size of your laser compared to single mode laser? Because this is really critical for some applications, I guess.
Yes, so because it's single mode, it really depends on the optics. So depending on the...
Yeah, but if you have the same, you have the same optics, how much bigger is the spot size compared to a single mode laser? Is it 2 times as big, 3 times as big?
So I think the answer is that you have, depending on the model of the laser, so example in the OPA6, you can have what is called the main lobe, and then you can steer it or move it in a range of 6 times the main lobe. So if you use 50 micron as the main lobe, you can steer it around in up to 300 microns. So you can, I hope that answers your question.
I think it does, because I think he was expecting for that answer. I think Tim from Hamburg wants to follow up with you on this. Thank you very much, all of you, for that fantastic Q&A. We continue the Eurovision tour, and now we go to Prague. We go to Hilase. I'm very happy to have Hilase because it's one of the key companies, one of the key members doing the R&D all the way to actually manufacturing their own lasers. Jan, thank you very much for being with us from beautiful Prague. The floor and the attention of everyone in the world goes to you.
Okay, hello everybody. It's a pleasure being here. My talk is also on laser shock peening, but I take a more general approach to it. So is this the, let's see, can you see the laser pointer?
Yes.
Yeah, okay. So my name is Kaufman and I'm from the Hilase Laser Center from Czech Republic, from Prague. And I'd like to say a few words about the laser shock peening technology we are offering here. So what is laser shock peening? It's basically code working process that uses high energy pulses, as we have heard, nanosecond laser pulses to create plastic strain, which in turn creates very deep compressive residual stresses. So the way it works is that the laser pulse comes from the right over here. It is focused onto the workpiece, which is covered by some kind of sacrificial layer. It can be black paint, it can be black tape. And there's also this thin water layer flowing on top of it. The laser pulse is absorbed and plasma is created. And the plasma is basically overheated gas, which expands very rapidly, sending high pressure wave, shock wave inside the material and causing plastic deformation. I'd like to stress out here that it is a cold working process, which means that no heat gets transferred from the explosion over here to the workpiece over here, thanks to the sacrificial layer that absorbs all the heat effects, and what is left is only the pressure that causes the plastic deformation. The result you can see over here. When you want to treat some larger area, you need to place the spots next to each other, because as we have heard, each spot is about, let's say, 2 to 4 millimeters big, and when you want to treat something bigger, you just create this this pattern. And if you want to do it, let's say, with circular laser, you can also overlap the spots such that you increase or you achieve more uniform coverage. Where is laser shock peening useful? Well, it's mostly in applications that are somewhat related to cracks, cracking and crack propagation. So mostly material fatigue, fatigue life extension. You can use it to prevent stress corrosion cracking, and also a new big area that is being opened right now is the additive manufacturing, which we have already heard some questions about, which is associated with the micro cracks that are associated with the process. The closest thing we have to laser shock peening in industry right now would be shot peening, which is very similar, but instead of laser pulses, you use these high velocity balls that basically hit the material and create this dimple, this plastic deformation, which again causes the compression underneath. There are a few key differences between these two technologies. The first one, I'd like to point out that the compression depth caused by LSP, the laser shock peening, is much, much higher than when it comes to shot peening. It's usually up to a few millimeters. It can say 1 to 3 millimeters. This really depends on the material, the thickness of the material, while in the case of shot peening, it's very superficial. It's just surface, basically. You can also see it on the graph over here. This is the depth of the shot peen part. This is the depth of the LSP part, but this difference tends to be much greater. The next difference I'd like to talk about is the roughness you achieve after the process. So in case of shot peening, the surface tends to be rather coarse, as you can, for example, see here, and some kind of post-processing is very often required, while in the case of laser shock peening, the roughness is not so bad, and it's rather smooth, and you don't need any post-processing after that. And the last thing I would like to point out in this section is that there is a very unique characteristic of laser shock peening that since it's a beam of light, you can actually use it to treat parts in very hard to reach areas. You can use it to treat some complex geometry, some cavities, which is impossible in case of shot peening, which relies on physical medium, which are the shots. So this is, that would be that. Now, when we come to LSP in the aerospace industry, there is a very rich history, because actually the very first commercial application of LSP was in aerospace industry. It was in the American military, specifically in 1998 on the B-1 Lancer bomber. So the problem was that due to foreign object damage, engine blade would break off and destroy the whole engine, because some stone would get into the engine and make a little chip in a bad spot on the blade, and the crack would start propagate, and eventually the blade would break off. And back then they tried everything. They tried shot peening, nothing worked. And then eventually they tried LSP and it worked perfectly, and they have been using it ever since. So the goal of LSP in aerospace industry is rather straightforward. It's mostly used to prevent costly failures, which is also associated with passenger safety, because costly failures, these failures tend to be very catastrophic in aerospace industry, and also decrease downtime where the plane, you don't want to have it grounded for too long. I would also like to add that this problem is not only happening in military. This is actually modern problem. Over here on these two pictures, you can see two different commercial flights where a blade broke off and destroyed the whole engine, and emergency landing had to be made. This is actually a picture taken by one of the passengers mid-flight. So you can see this is very up-to-date problem, but this is not only related to engine, engines, it's also related, for example, to wings themselves. There was this accident where there was this little plane which would do a lot of maneuvers, a lot of cycling, a lot of cyclic load, and eventually the whole wing would come off and the plane would basically crash. So all these things are related to the fatigue. When it comes to the implementation of LSP in aerospace industry, there are two ways how to do it. Either you can do it during the MROs, which is the maintenance, repair, and overhaul. This is, however, very challenging because you are highly time limited during the MROs. You're not the only person working there, so it's also very demanding on, say, cooperation. Also, you need to bring the laser to the plane. You can't bring the plane to the laser. So this is also very, very challenging to actually create a portable LSP system. And there are extremely high safety standards. So maybe easier way would be to introduce LSP into the manufacturing process, where you integrate it strictly or directly into the process itself. And that might be an easier path to take. When it comes to LSP in naval industry, the idea or the philosophy here is to basically reduce maintenance costs, reduce maintenance in itself, and also reach some fuel savings through lightweight structures. So when you have more lightweight materials, you tend to reduce the material, and some of these, let's say, joints become weaker, and that's where you can use LSP to strengthen them in these critical areas. Over here, we can see a graph which tells you number of stress corrosion cracks over a course of 25 years on this Ticonderoga class ship. And you can see that since the 1990, the number of cracks per inspection has been steadily increasing. And this problem, we can assume it's going to be increasing even more. So this problem is not going to go away. It's going to be more and more urgent. So this is where LSP can help a lot, because in order for stress corrosion cracking to develop, you need three components, which are susceptible material, corrosive environment, and tensile stresses. And LSP can help with the tensile stresses. It can change them into compressive stresses, which renders the whole stress corrosion cracking process, basically, it doesn't work. Another area where you can use LSP in naval industry, this is something we have actually done at Hilase. We've tried to reduce cavitation effects. So cavitation is basically when you have these low pressure bubbles imploding against, let's say, ship propeller. This is the damage it does. So what we've done, we took a water pump blade and we pinned it over here where the cavitation is most severe. And when we've done some experiments beforehand, we've pinned this disc over here. You can see these 4 LSP patches, and we have subjected it to LSP to cavitation for a period of 100 hours. And then we have measured what the cavitation did, and we found out that actually the mass lost due to cavitation, also the depth of the cavitation was halved in both cases. So this is just an example for you to how to think about the LSP process. And my last slide is about our Hilase facility capabilities. So what we are offering, we have our own LSP station, which you can see over here. We have a state-of-the-art laser system, which can deliver, not now it can do 7 joules, but soon in the future, it might be 100 joules at 10 hertz frequency, which is unprecedented. We also, there is a limitation for the samples we can treat, which is 20 kilogram load capacity of the robotic arm. And we also offer some kind of, let's say, I call it midway sample characterization, because we are not equipped to do the fatigue testing or strain tests or anything like that, but we are equipped to do the residual stress measurements. We are equipped to do some electrochemistry. So the way it usually works here is that a customer comes, they bring a specific problem they are facing in their own factory or industry. We take a look, we try to use LSP on it, we try to optimize the process, and then we send the part back to the customer who tests it in their own environment on their terms. And if they are satisfied, we can keep on with the cooperation and see what comes next. So that is everything I wanted to say, and I'm ready for some questions. Thank you.
Thank you, Jan. Thanks a lot for this overview. So it's great that you could put together the two applications. So it's a nice place to be. So this opinion, I'm also happy you didn't say, you said that the lasers are better than the spheres, because I was scared there, but good that you were playing for the lasers. So thanks a lot. So you a bit addressed the EPIC questions. So the question would be, so you offer a service, right? So your room for collaboration here in the room is, please come to us and so bring problems. That's basically what the
this is what we say. Also, when it comes to LSP, the problems tend to be very, very specific. So very often, you know, when let's say when shot peening would do the work, there is no point doing LSP because shot peening tends to be cheaper. So it needs to be a very specific problem which cannot be solved in any other way, I would say.
Very good. And then do you think, so you showed your equipment. So is there something that you would like that could help you from your, let's say, manufacturing side of the supply chain that can help you with, or you are happy with what you have? I don't believe that.
We would definitely like to expand our, let's say, testing capabilities. So I said we are missing all these fatigue machines because they are just, we wouldn't use them, you know, they wouldn't pay for themselves. So it would be nice to have some kind of collaboration where we would send this tests, where we would send the samples to be tested and then send back. Well, I mean, these end tests like fatigue testing or slow strain rate testing and all these kinds of tests.
Okay, and then last question from my side at least, but please, of course, ask if someone in the room wants. And you have these nanoseconds, so a few nanosecond lasers mostly, right? So, and we heard before there is this debate: should we go shorter? Should we go longer? No, should we go shorter or not? So, is it for you the sweet spot for all these applications you heard, or you also want to go shorter?
We have 10 to 40 nanoseconds. I think the sweet spot is somewhere around 15 to 20, as we have heard. And basically, if you have the pulse longer, you can achieve greater depths of compression. But there's an upper limit for that. So it's a tricky thing, and this is also heavily dependent on the laser you are using, and also on the spot size, and also on the intensity distribution. There was a question before how it affects the process. So I would say that, you know, the larger the spot, better. And what it does, actually, we have uniform intensity distribution. The shock wave that propagates inside the material tends to have planar character. So let's say it gets weaker planar, you know, the dissipation is slower, while if you have all the energy concentrated in the middle, or the spot size is very small, then you don't have planar propagation. You have more like a radial propagation, which means that the strength of the wave falls off much faster with a square root of distance, unlike in the planar case where it's 1 over r, you know. So it goes deeper and you can achieve higher depths of compression.
Okay, and last challenge for the optics developer here in the room. Do you have it with so much energy, or you're already satisfied with it?
When it comes to laser, I think we're fine, because part of our laser facility is we build our own lasers. So we're fine in the department. What we're looking for more is the collaboration in the manufacturing process. We are looking for specific problems, for specific applications we can use our lasers on.
Very good. Thanks a lot, Jan. Now I wanted to give a bit the word to someone that from your end user cases from the aeronautic side. So I know we have in the room Ivan from Avio Aereo. Are you there? There you are. Thank you for joining us today. Could you maybe introduce briefly yourself, just to say a couple of words about Avio Aereo and your interest in this meeting?
Yes. Good afternoon, everyone. Can you hear me?
Yes, all good.
Okay. Just a few words about Avio Aero. Avio Aero is part of GE Aviation company. And so looking at what you presented today, I can say that we see a lot of applications that are related to our business. We produce combustors, and I can easily see the application that Mohammed showed at the beginning of the meeting, and we also have parts that are shot peened, not laser peened, but shot peened. And let me say that we could have, we could have much improvement in that. using that technology. And we say that this is the first time that we participated to this meeting, and this is a good opportunity to have an idea from all the possibilities and offers that are on the shelf in the market and can be leveraged for our business. Thank you for this opportunity.
Thanks a lot. And then we said already, he didn't say it that he will think about it, Jan, or all the laser pinning experts, but let's say he's getting curious, Civan, right? So thanks a lot. Thanks a lot for your contribution. And now it's time. I'm really looking forward to the contribution from Marius from Damen. So now we are approaching slowly the shipyards industry. So it's really a pleasure to have you here, Marius. So the floor is yours when you want to start to share your screen.
Hello, everyone.
Hi.
Just now I will share my screen.
Yes, please.
Just a second.
Green button. Yes, something is coming.
So, yeah, can you see it?
Yes, presentation mode. I know you're clicking it.
Yeah. So
there you
we
go.
are a shipbuilding company. Basically, we are building different types of ships, very diverse ships, from let's say 20 meters to 200 meters, and ships that are tugboats, that are yachts, that are navy vessels, that are offshore vessels. We are currently in the process of building a navy vessel for the Dutch Navy, a vessel of 170 meters. And of course, also we have 2 yachts in progress. So basically we have quite strong demands of quality. We also think that in the future we will need to implement lasers. Don't know if in the near future, but somewhere in the future. And we are thinking where to implement them. We have some issues on deformations for the tin panels. So this is the current challenge of the shipyard for the tin plates. Sorry. And in general for the vessels like yachts, they are composed of tin plates. And they have a high demands of productivity, so we can be very efficient and competitive on the market. So basically, we are thinking that laser can be an option. Laser in terms of laser for welding or laser for cutting. And if we are speaking of welding, then I suppose it will be a hybrid laser from a conventional welding process and a laser, and this should offer a high productivity and quite a good quality. Also we know that the laser has some negative aspects. We have high demands of joints preparation tolerance if we are using laser. So to be able to execute a good weld, then you need to have a perfect cut of the plate to have a good joint. And also is the highly priced compared to the conventional welding or cutting process. We know also that there is a risk regarding the high hardness values that can be found on the base material if we are using lasers. So this will be, let's say, like a negative approach for using the lasers. I have put also some sketches with the types of panels that we consider that could be executed with a laser process in terms of cutting and welding. So you can see here different shapes of the panels. The joints consist of the butt welds between the big panels and fillet welds between the profiles and profiles with the base plate. So this is the base plate, yeah, and here is the profile that are put on every panel. What is the range of the plates? We are working with thin plates. Of course, this is the thin plates in shipbuilding. Can be also thinner, but considering shipbuilding, thin plates are between 4 and 8 millimeters, and it goes up to about 30 mils or even 100, depends of the situation. The material grades are A or EH36. This is a material grade for ship building, and as I said, when you are working with higher material grades, you have a high risk to have a big harness on the area that you have cut or welded with laser or hybrid laser. So that is a negative approach. The material dimensions consist of plates and profiles. Plates can be from 4 millimeters and 200 by 400 and smaller, to plates of 15 times 3000 times 2000 and bigger than that also. But this is the area where we are situated. Profiles consist of angle unequal, Holland profile, and flat bar, and you can see them here shown that what is the shape of those profiles. The weld types consist of fillet welds and butt welds, and now we are working with welding processes for submerged arc welding, for flux core arc welding, for solid arc welding, metal core arc welding, tungsten arc welding, and stick electrode welding. And as cutting process in the shipyard, we have oxygas and plasma cutting. Here I made also a sketch. I took out a sketch for the joints that we have for the moment. So basically what we will need in the future will be an equipment that could weld this type of panels with a good quality, low requirements for the joint preparation, and of course to be as possible on a low budget price. Yeah. For the future, we are also thinking about investing in other processes in the shipyard, and I made here a sketch. We have the green smiley face are the preferred ones that we intend to invest in the very near future, so maybe next year. And we already start investigating the micro panel line. Micro panel line, what does that mean? Is a panel, as I shown you before, but of smaller dimensions, not more than 12 times 3 meters. So let's say smaller panels, that's what I have shown, and executed on a panel line like this here in this sketch. So for now we are investigating this situation, and I suppose that sometime next year or the next one we will invest in a panel line like this. This micro panel line will have the first station consisting of an assembly station, and the assembly station is this one that will pick up the profiles from cassette and put it on the line. The line will be the panels will be on a conveyor that will go with the panels in the production flow. So the assembly gantry will mount the profiles on the base plate, and the conveyor afterwards will bring the profiles that are mounted on the base plate in the area where the welding robot gantry will weld the profiles on the base plate. Eventually, after the robot gantry will weld the profile, the panel that is welded will reach a station where a final adjustment will be made for, I don't know, slag removal eventual repairs or whatever will be done by a manual welder. Of course, we are thinking of investing also in a pipe workshop. You see here in the sketch the pipe. Basically, the robot will take the flange and mounts it on the pipe and weld it with a conventional welding process. We intend to invest also in a small steel workshop. Then also, as you can see, it involves all of this involves robots, so it is a robotized process. And we intend to invest in the, let's say, very near future, step by step. And all these investments need to have a base. We need to make a business case for every situation and to make it feasible for the shipyard. Yeah. So basically, for now, I suppose what we are looking is to find suppliers that can offer us solutions for lasers, but also for robotized welding and applicable for shipbuilding, of course.
Marius, you can't imagine how happy I get when you say that you're looking for suppliers. Thank you very much for a fantastic presentation. Lots of room for cooperation here. I do love it. We can talk a lot about the different room for cooperation, but I'm going to ask you first about a particular challenge. If you could share with us a challenge that you think, oh my God, if I find a solution for this after this meeting, I'm going to be the happiest end user in the EPIC network.
Well, a particular challenge, I think it will be also the deformations that are coming on the plates from sandblasting, because the plates need to be clean before painting, so they need to be sandblasted before, and the equipment that we have now deforms the plate, and of course afterwards we need to straighten the panel. So basically what we will need, it will be an equipment that can clean the plate easily without deforming it, and afterwards to be able to make it straight again if it is deformed.
All right, so the challenge is on the table, and I'm sure there are many people who would like to address it, and I have people already smiling in the room who want to get in touch with you, but I want to go with you together to Lausanne. I want you to meet one of the system integrators in this network, Alejandro De Quero from GF. Alejandro, thank you very much for joining the meeting today. I know that you are an expert in the laser texturing. That's the key part of your supply chain. You saw the presentation from Damen. Is there any potential room for cooperation?
Hi, Jose. Thank you. Hello, everyone. So, well, we are not that active into the naval industry. I'm coming more from the aerospace world. And actually, GF Machine Solutions has several technologies, not only laser texturing. We have also milling machines, EDM machines, additive manufacturing. And when it comes to laser, we have several already some applications proven in the field, especially in aerospace, what we have seen before with the drilling holes for cooling applications on blades and combustion liners. We do that. In naval applications, I will have to check, and I'm afraid that especially on welding applications, we don't have any particular machine that can help Damen on that. However, our product portfolio is open to anyone in the room, so I'm free to be contacted if you have any question.
Thank you very much, Alejandro. George Fisher is a key company in this ecosystem, so we always want to for the person who from GF to say hello. But I'm going to go back to Marius. We have a few questions for you. The first one is coming from Lava X from Benjamin. Benjamin, what's on your mind?
Good afternoon from Aachen. I'm with Lava X, so we developed a process called laser beam welding in vacuum. And we also developed a process which is called laser beam welding with mobile vacuum. So the vacuum chamber moves alongside the welding process. And therefore it's possible to achieve a penetration depth of 20 millimeters with nearly 6 kilowatts of laser power. And I was wondering if this process might be suitable for your applications.
Yeah, I think it is. I think it is something that can be used here, but for much better investigation, if you can send me a flyer or a brochure or something that details more the process and how it works, maybe also some information regarding the quality, regarding mechanical tests that the process offers for different material types, different
Yes,
base material types. That will be
I'll
very
write
nice.
you a personal message, and then you can give me a contact.
Fantastic, Benjamin. Thank you very much for being with us. Marius, get used to this. Many people are going to be contacting you after this meeting. I have 2 questions to ask you. So about the welding is very clear. I would like to know, is there any room for cooperation in, for example, anti-fouling surfaces using surface traction?
We are not doing something like this. We are not doing things like this. No, no.
And how about laser cutting? You talk a lot about welding.
Laser cutting can be also a possibility in our shipyard. Yeah.
Antonio Raspa is the innovation manager of EPIC, and he's really very happy with that answer, right, Antonio?
Yeah, I think that, but just for all the people in the room, when you speak about laser cutting, which are the dimensions of the sheet and the thickness of the sheet?
Well, as I said before, we have a very large scale of dimension, and we are starting from 4 millimeters, and we can reach up to 100, maybe also bigger than 100. But the large variety is somewhere between 7 millimeters and 30 millimeters thick plates. Yeah.
Thank you very much for a great presentation. Marius, was your first ever EPIC meeting? The first of many, because you are a star. That was a great presentation. Thank you very much. We continue with the program and we go to Rostock, SLV Rostock. What a great company to have. Rico Peters, Managing Director of SLV Rostock. The floor and the attention of everyone on this great meeting. By the way, thank you all for all the feedback that I'm receiving. Is yours.
Yeah, thanks a lot for the opportunity. I'll just share my presentation. Just a second. So you can hear me?
Yes. And we'll go to presentation mode and we'll be ready. Yes, perfect.
Perfect. So I will also go into the topic of shipbuilding industry. And let me start just to give a short explanation what we are doing. So we are a research institute in the northern part of Germany, located in Rostock. We have about 35 employees here. With a revenue of roughly 4 million euros per year. And we belong to the DVS group, which has about 850 employees all around the world, mainly focused in Germany. And within our company, we have 3 big parts, which is the research and development, which makes about a third of the whole revenue. The services, which means also small series production, as I will show afterwards, and the education and training, which is, of course, always important. For the companies, if you want to introduce new processes, you also have to train the people. We have a lot of laser equipment here, starting from conventional, let's say big lasers like 12 kilowatts disc lasers, 10 kilowatt fiber lasers. But for our customers, we are also working with 20 kilowatt diode lasers from Laserline, for example. And if we go to smaller parts, we work with pulse system in the green, in the infrared, down to femtosecond lasers and picosecond lasers for special surface treatments, as we have heard also today. So many of these laser systems are combined and with handling systems, CNC based and also robot based. And the idea that we can combine all the laser sources with the different systems to get a very easily access for our customers to real production lines. And this means, as we have seen also in the last presentation, that, for example, a shipyard can come to us, test their problems and their processes. And after that, they can say, okay, what is the price per meter weld seam, for example? And of course, to use all the things, we have to have some analyzers, which is, for example, scanning electroscope, microscopy, laser scanning microscopes, and so on. And so the topic is how we work and what do we do. In principle, we understand us as a problem solver. And we can offer to our customers and to our partners research and development from really first trials, for example, here for laser welding and laser hybrid welding, to set into operation. And we have seen this type of systems before on the last presentations. This is a laser panel line, which was built by the company IMG here from Rostock for partners in Italy, namely Fincantieri in Monfalcone. And together with IMG, we developed the laser processes, parts of the laser system, and also after that, we were doing the staff training and the certification of some special processes here. And this system is used in Italy since 2007, and afterwards there were several other systems also installed in Italy as well as all over the world, namely Russia, China, United States, and so on, from the same manufacturer. And in this topic, so that is the way we work, and we work in this way in different research topics. So we can divide it, for example, in the basic or fundamental research, which means it's typically public funded research projects. If the customer and the companies want to have a fast track, then we can also do contract research. This means in comparison to research and development with public funding, which is usually in the area of 2 to 3 years, you can do this contract research where you have a result and process developed within 6 months, for example. And if the company says, okay, that's a nice product and a nice process, we can also do services and small series production until the own system, which is developed, is then installed at the customer sites. And these 3 fields, we are working in different topics, which means laser welding, as I have shown before, also additive manufacturing, which is a quite big and strongly growing part. So we have also seen some of these applications also in the former presentations. For example, here the repairing and 3D generating of special turbine blades, for example, and also the laser microprocessing is a topic which has been far growing in the last years, namely in femtosecond and picosecond laser systems, where we are doing topology and surface functionalizations on big scales. And of course, you cannot do something there if you don't have a materials research, which means that we have a lot of analysis. And for example, also maybe it's interesting for Jan from Hilase, we are doing also fatigue testing of different parts for ship propellers and propulsion systems and so on, and doing the several fatigue tests as for bearings. And at the moment, there are certainly some fields of interest where we have a focus on. First one is the laser welding of special profiles. On the left side here, we see a single pass laser hybrid welded profile with a thickness of 25 millimeters EH36, as we have seen in the last presentation. Here the welding speed, for example, was 1.3 meter per minute, which is quite high at this high thickness. For example, if you weld 5 to 8 millimeters, which is common in cruise liners, for example, cruise liners production. Today, state of the art, I would say, is between 3 and 4 meters per minute welding speed. Of course, you have some issues with the hardness, but with sophisticated and stable stable processes, that's I think not an issue anymore, and is widely used in automotive industry and shipbuilding industry. One interesting point is that you can use not only static and large systems for this welding. We also have developed together with partners like Trump, Fronius, and also other companies, mobile equipment, which you can see on the left side, where we can weld up to 12 or 15 meters of panel lengths with a mobile tractor equipment, which is fiber coupled then to the laser and can be used within the yard. And of course, you always have to think about what is the most economic way, also in terms of laser safety and so on. And these both pictures on the left side, they were both a result of a project, for example, with the Maya Yard in Papenburg, Fincantieri in Italy, former known STX in Toku, and also the colleagues from Damen were involved in this project, which is now, I think, 5 or 6 years ago. And also we are transferring this knowledge from the shipbuilding industry to other industries like steel building or architecture. So on the left side, you see also a cross section of a bridge with a width of 4 to 5 meters and the length of 20 to 25 meters. And also with this high power lasers, you can weld these sandwiched steel plates, which are known from I-core panels, for example, from the Maya yard, also can be used for bridges or for architecture. In the middle, you see the additive manufacturing of complex structures, which is a fast-growing field in our house. Starting from large non-standard systems where we can weld up to 6 to 3 to 2 meters in printing volume. We are developing for this because we are using usually laser powers of more than 10 kilowatts, sometimes also 30 kilowatts. As you cannot buy so many optics for this, we had to develop our own optics and cladding nozzles. And we are doing this in a service also. And since this year, we are also producing our own powders for laser cladding applications and laser powder bed fusion for special alloys, where we are able to produce above 10 tons per year of own powder. And for this laser cladding, for example, we are using at the moment between 2 and 3 tons per year, just in the case of services and research and development. And on the right side, the third topic, which we've heard also today about, is a picosecond and femtosecond laser surface structuring, where we had a big cluster project at the moment where we are surface structuring, for example, implants like hip implants or dental implants. And here the aim is to do a scaling to large scale applications, also for shipbuilding industry, for example, where we have projects at the moment. We're dealing with anti-fouling surfaces made by laser functionalization to get rid of these chemicals which you have to need for anti-fouling surfaces. And the physics behind this is nearly always the same. So it's so the bracket is always in the laser, and depending on the application, of course, we have to look for the right laser and for the right process at all. And of course, not every hammer fits to every nail. As we are always discussing. So, for example, if you have a standard arc power welding machine and it's cheaper with the same output like a laser, of course, then you should stay to the conventional process. But for example, also for the talk from Marius, there were some very nice studies in the last years from companies like IMG or Prima and so on. And they've shown that for a standard cruise liner, which, for example, is built in Papenburg, they saved up to 2 to 3 million euros per ship just due to the less deformation and to a lot of save time overall when they use laser instead of conventional MAC welding and or TIG welding or whatever. And at the end, this saves a lot of money, and this is always a very interesting point to look at. Okay, and that was the point from my side.
Rico, thanks a lot.
Nearly in time.
Nearly in time. Now, thanks a lot, Rico, for your contribution. It was really a nice and intense slide, the last one. So really nice to show what the SLV can offer, and also you related already to other contributions before. So it's really great. So I knew also that being my laser guru at the beginning of my PhD, I knew you would have spent a few good words about lasers and not the traditional welding and other traditional technology. So it's really nice to have you here. So you said already a bit of your, let's say, what can you do for them? So what you do for them, you said it. So where do you see collaborations here also in the room?
Yeah, so for example, one big point is, as I also see the question from Christophe from Thales, exact one point is if you go to scaling for large surfaces, you of course need high average powers. And at the moment we are trying to invest also into laser sources in the femtosecond regime with more than several hundreds of average power. And of course, if you want to have a surface functionalization of a whole ship hull, then you would need, I would say, at least several kilowatts of average power to get a process which is cheap enough to come into the market at the end. So in the best case, I would need 5 kilowatts, 400 femtoseconds. That would be perfect. and in the
Okay,
megahertz.
because I tell you, what we have in Lampas, that is also an initiative, also a European project, we have a few picosecond, but a bit less kilowatts, so like 1.5 kilowatts for a few picosecond. Maybe we don't cover the ship, but we are on the way. So our aim is to cover large surfaces with a high throughput and without too many, let's say, different levels. So a flat area, so on the side of the ship, it could be, of course, a very convenient one. So let's talk about it. Lampas. So we have also here, if there is some, actually, I know there is Jose here in the room, the other Jose, that is the the Lazea Jose. So Jose, if you want to comment about something now or never, otherwise I already advertise our Lampas project.
I think you already said it's a quite interesting project, and the reason to remain in picosecond and not going down to femto is because we handle interferencing of the beams, and we need certain lengths of coherency. But otherwise, there are other initiatives also related to kilowatt range femtosecond lasers. But yeah, it's on the way, still in R&D.
Yeah, still in R&D, but close to service at least. So keep an eye on our website so that Lampas is developing, getting to a final product finally. So now I have also a question. So you mentioned, Rigo, laser line in your list, and we have here Johannes in the room. So Johannes, can you unmute yourself? Tell a bit your collaboration with Rigo and with other potential customers of yours, and also on the manufacturing side, of course.
Yeah. Hello, everybody. So my name is Johannes from Laserline. We are developing, producing diode lasers for all types, for several types of applications, hardening, brazing, cladding, welding as well. So on today's topic, we are also developing and delivering lasers for naval shipyard industries. So that's the point where I also want to step in contact with Marius Calmuc after this meeting today. So we are offering lasers up to 60 kilowatt with different kind of beam shapes, also in combinations with GMA hybrid welding and also with cold wire welding. So benefit we're offering is by our diode lasers, by the beam profile, that we can reduce the hardness peak in the affected zone, which was already mentioned here. That's also a point which lots of our customers are requiring. So maybe we can step in contact with that later after the talk.
Great. Thanks a lot, Johannes, for the introduction. So now I know you are really potentially end users also for future events. So let's not forget that we have next year an event on robotics. And I see Marius, Rigo, they keep saying they need robots. So let's talk about this also soon in Q1 of 21. But now let's stay here on the naval application. And let's go finally, because I on purpose didn't talk about it yet. Additive manufacturing was mentioned a few times already, but I thought let's optimize and wait for Tim's contribution so we can a bit go deeper to the additive manufacturing. So we come here close Hamburg, because Rigo left Hamburg for Rostock, but we have here Tim sharing his screen. There you go. You're maybe muted? Yes.
Now you can hear me, hopefully.
Yes, very well.
Okay,
there you go.
perfect.
The floor is yours.
Yeah, thanks a lot for the introduction, and very welcome also from the northern part of Germany, from Hamburg. So I would like to give you a short overview on the Fraunhofer IAPT. So basically trying to answer all the three questions of today. So what are we doing actually at the Fraunhofer IAPT? What is our core competence? What do we offer in the field? And what are we looking for? So what kind of cooperation is usually interesting for us? So yeah, my name is Tim Wischerop. I work here at the Fraunhofer IAPT for over 8 years now in different positions. Actually also headed the aerospace additive manufacturing design team for quite a while. And since almost 3 years now, I'm the head of the AM design division. And yeah, really happy to give you a short overview on our institute. I guess that probably most of you here in the call basically know Fraunhofer. It's the biggest research organization in Europe, and what we are doing is applied research. So we really try to help adopt the industry new technologies to the best needs. And Fraunhofer is organized in different institutes, and each institute has a different core competence, I would probably call it. And we are the Fraunhofer IAPT, so Institute for Additive Production Technologies. So everything that we are doing is somehow related to additive manufacturing. And our mission basically is to try to help the industry to industrialize additive manufacturing and use it for their components and for their processes. And we think that's a really resource efficient and green technology. So we try to also emphasize that. And we're located in Hamburg, as I mentioned before, and we are around 100 employees working there on different additive manufacturing technologies. For Fraunhofer, 100 employees is not a big institute, but if you look in the field for additive manufacturing, we are probably the biggest research institute looking on and focusing on additive manufacturing. We have a quite big variety of different additive manufacturing technologies, but our biggest competence is laser additive manufacturing. So laser powder bed fusion, laser sintering, laser metal deposition are the laser additive manufacturing technologies we have here in-house. And we focus on different markets and aerospace, automotive, tooling, and medical. So that's basically what we're doing, trying to further develop the technologies and help the industry to utilize additive manufacturing. So what do we offer? We actually have a big, can offer a big variety of different services to the industry. We have quite some history in basically working with smaller companies going into additive manufacturing, basically enabling them by trainings. We have a lot of different trainings that we do since 7 years now at the Institute on additive manufacturing, different courses. We help companies to identify the right parts. So where can you utilize additive manufacturing on the best way, doing specific material or process qualifications, have a lot of experience in doing bionic designs, new designs with additive manufacturing. But we also work a lot with machine manufacturers and really established companies in the field of additive manufacturing to further develop the technologies and making the next step in additive manufacturing. And probably most of you already know that there are a lot of advantages we can take from additive manufacturing for the different markets, like low material weights. We have really good mechanical properties. But from my point of view, and as you probably know from my title, I'm the head of the design team. So I really believe that the most important advantage we have in additive manufacturing is the big design freedom that we can use for our different designs. And you probably know a lot of examples where you use these design freedoms for bionic designs, for lightweight designs in aerospace industries, etc. But I think the real advantage actually is in the field when you try to combine these lightweight design potential with other functionalities that you can optimize in a specific part. And here are just some examples that I wanted to highlight in the short time that I have. So for example, optimizing the cooling in heat exchangers by optimizing the flow of the material and the structure of the component. You actually can optimize your acoustics, vibration or damping of a specific component, as we see it here. So this really is one of our core competences that we actually have, utilizing the design freedom we have in additive manufacturing to basically increase the performance of different parts. And I can imagine that probably in a lot of different applications there is the potential, and usually it only pays off if you actually tackle these. So this design is one of our core competences. Another thing that I wanted to highlight is our competences in optimizing the AM processes themselves. So we have a lot of examples where companies come to us and they actually have problems with the quality of a specific parts, or the parts are too expensive, so they need to increase the productivity of the process, or they want to have a specific material for the part that's not available for additive manufacturing. So what we actually do then is trying to help them to optimize the process in a specific way so that it actually meets the good requirements of the customers. And here are just some examples of things that we do, trying to optimize the stability of the process. For example, by beam shaping, which we already discussed earlier, developing faster processes, trying to locally improve the mechanical properties of parts. So these are just small examples. Obviously, I can't go into too much detail. So the last question is, what actually are we looking for here at the Fraunhofer IAPT? And basically, there are two different categories that I would like to highlight. First, obviously, we are looking for companies that are trying to use or implement additive manufacturing in their company. And yeah, maybe you're at the start and want to know, is additive manufacturing feasible for my products or not? We are happy to help with that. We actually do free part screening. So basically evaluating if there's a technical and economical sense to use additive manufacturing for your specific parts, or you already use additive manufacturing company, but have specific problems with additive manufacturing, maybe in the quality stability of the process. We can try to help you with that. On the other hand, we are also looking for companies that have special capabilities and products, especially for laser additive manufacturing. And because we think that there is quite a lot of things that can be optimized in the process. Here are just some examples. For example, if you have special lasers that might be worth testing on additive manufacturing, ring mode lasers, specific wavelengths of the lasers to improve the process. Or you offer specific optics like beam shaping optics, optics with a low thermal shift in the process. Or you have specific sensors that might be interesting to test for quality assurance in additive manufacturing. We are happy to try that out with you and see if there actually is a market opportunity for you. Or maybe there's even something else that I haven't mentioned and haven't thought about, and you think in your company it's worth trying. Take a look. If there's something for additive manufacturing, I guess we are a good start to take a look into that.
Thank you very much for a great presentation, and thank you for being here. I really would like to add something to that, which is that TEAM and Fraunhofer IAPT is our entry point for testing any technology for additive manufacturing. So anything, if you have nice beam shaping optics, powder, new materials, new ideas for 3D printing, these are huge room for cooperation, and we really love that Fraunhofer IAPT, all the way from Hamburg, Germany, is part of this network. I would like to explore perhaps some room for cooperation with my friends from Damen. I know Additive Industries is in the room. Welcome back to the meeting. Did you see the presentation from TEAM? What kind of challenges do you see in the 3D printing that we need further R&D?
Well, actually, yeah, so you can hear me. So challenges in additive manufacturing are, I think they also have been proposed, touched upon by the IAPT presentation. It's about process control, predictability, and repeatability in our systems, in the process itself. And specifically, the holy grail is let's say, a continuous controlled feedback loop with your laser that's in your melting pool. And that's where we still see quite some challenges in just in technology solutions to be conquered. But that is if we have, let's say, a fully controlled melt pool with a feedback loop with predictable material characteristics, that really would drive, would increase the confidence in the technology. That would, of course, drive the business opportunities.
Thank you very much, Harry. Thank you, well. The thing is, Tim, that we have companies in the room like Nuburu, that they really are pushing for additive manufacturing technologies, like AMS technologies, like the guys from DMC in Lithuania. So I think after this meeting, lots of room for cooperation is going to start. But we're going to move to the next one because it's the hottest topic for me. I love it. Laser cutting. And we have Soitap in the room. Emmanuel. Good afternoon. Thank you very much for being with us. This is the cool topic for me. The floor is yours.
Good afternoon, everybody. I try to share my video. Do you see everything?
I can't wait. See it crystal clear.
Yeah, perfect. So thank you very much for everybody. And really thank you from Marius, Damen, that when I heard next year we want to invest, this is very lovely for us. I belong from sales. Who we are? We are Soitap. Soitap is one of the oldest company in cutting machine, CNC cutting machine, for steel plate cutting machine, belonging from 1938. And he had the first laser machine, cutting laser machine, 1983 in the CO2. And then we went back to the fiber early in 2011 also. many times ago, and we are Italian-based company in Milano area, where we produce almost everything inside other than laser technology in terms of source and optics, but we do the machining, which is our goal. Our goal is to create a CNC cutting machine on 2D for any kind of thermal technology, from oxy-fuel, plasma, water jet, and high-power fiber laser. What is our specific, how can I say, specific behavior, our specific cookie that we can give to the market? The market is the fact that we have an internal capability of a large dimension cutting machine. And specifically also in a laser cutting machine that's for steel plate, and in particular for the Navy industry, shipbuilding in particular, we can also provide from 12-meter machine with a changing pallet, even higher with a different possibility of, let's say, not changing the pallet and moving the material, but like a standard plasma machine in a long size area, we can cover up to, let's say, 48 meter for cutting material, specific material for mild steel. What is the differentiation that we can provide to the market, and specifically on the Navy market, is the fact that we are really capable to have a bevel cutting, not only vertical cutting, but even bevel cutting. Bevel cutting on a steel plate, so we are talking about 2.5D dimension, not in a 3D dimension, but we uncover from the 0 degree, okay, the vertical one, to the plus minus 45 degree on a, let's say, mild steel application. Then we will see what are the strength and worst case on the naval industry. Here we have some of the latest application that we have developed on a laser cutting, starting from a vertical profile. So when we are talking about cutting for us material, we are talking about low thickness for us is for 4 millimeter higher. So 12 millimeter, 19 millimeter, 25 millimeter, 30 millimeter. That's have been provided with a specific, let's say, laser with a beam shaping processing. Why we did this? Because we would like to understand and to reach a sort of quality surface as much as similar to a plasma surface, so very with a low level of roughness. That is the vertical, but then we have provided also possibility of cutting in a B profile, Y profile for welding preparation. And there are some examples that we did on 20 millimeter mild steel, B profile 30 degree, or a Y profile, so with the 6 millimeter weld bead, or even lower. That's the point that we would like to really emphasize in the next future, to have a possibilities of Y and X profile with a sort of welding preparation, very accurate, narrow, and precise. So why we are interested in participating in this, let's say, in this meeting, or also in the field, is the fact that we are a company who has for a long time developed, let's say, classical thermal cutting like oxy-fuel and plasma cutting. But we think, as many of the players of the market thinks, that the fiber laser, specifically even in the middle high level thickness, it will become more and more applied or requested, specifically for all the possibility of a welding request. For example, the fact that a fiber welding can require some specific particular quality level, or the fact that the narrow edge or the bevel cutting has to be as much as possible and as much as possible precise compared to the classical cutting technology. This will, for sure, this is putting more emphasis and strength on the research of laser cutting capability with a wide range of possibility to cover, in a specific, for example, the shipbuilding industry, wide range of material thickness from, let's say, the 4 to the 30 millimeter, for example, and with the possibility of cutting with the beam shaping, we can ensure a less higher level of roughness, or let's say quality surface, with a wide range of material thickness, using, let's say, a sort of a middle range of high power laser, or even higher, or any way to keep the cutting quality constant, even not using the highest power that are available in the market. That is permitted thanks to the beam shaping possibility that are present now in the market. So going to the point and the end, what we ask for, what we can do, what are the challenge for us as a company who produce a CNC cutting machine for steel plate, and specifically on the shipbuilding industry. One of the highest challenges is the specific steel naval industry that is demanded by primarization on top. So what could be the, let's say, the possibility of the latest laser application on this thickness? What could be the quality, the cutting quality, and what could be the chamfer application on this specific material? So that's why we are looking for fiber laser solution, meaning in two ways: high power laser, or multiple power distribution, for example. And this brings also the question and the request of having an optical solution, meaning as much as possible high power cutting head, or cutting head who can manage multiple power distribution. And another specific and really target demand is the nozzle design, in order to not only cut in vertical, as we said, but also in bevel, and to permit our head to follow the bevel process. What we can offer in these fields, in this meeting: testing and application, because we do machining, we have machine in our labs. We can do so for research, for specific solution. In this meeting, we are talking about naval industry, and we are really deep in the naval industry. And we can do also technological comparison, because we are even plasma expert. So we really can think about, in the next future, to go to parameterize and to compare plasma technologies versus laser technology, considering cutting costs, let's say, but also investment level costs. This is what we offer, and this is what we really thank you very much for the attention and for everything.
Thanks a lot, Emanuele, for your contribution.
Yeah.
So it was clear, nice Christmas list. So fiber lasers, do you have maybe some more specification? You say high power, if you have a bit more of specs that we can share with the people here in the room, but also maybe give it also to the 650 companies?
Yeah, right, absolutely. We are really looking into the high power. That means, let's say, higher than 10 kilowatt, 10, 12, 15 kilowatt high power, that permit us to have a great performance in a, let's say, middle high level of cutting finger, let's say higher than 12 millimeter up to the 30 millimeter. And that can permit also the possibility of having a bevel cutting, even in the middle range thickness, but with higher, let's say, with a higher performance, because at the end it's always a comparison between productivity. And at the moment, the classical conventional cutting technology in the shipbuilding industry is not, let's say, the laser as a major focus on the cutting, on the long panel, long process, and whatever it is. So we think that in the next future, main, let's say, emphasis on the power or in B shaping can be really, really very interesting.
Very good. So beam shaping, we heard a bit already today early on. So I guess there is some good candidates for that. So we heard a few options there. Tiffany is nodding, so very good. But now we can maybe hear from what Giuseppe has to say from OPTOPRIM. So I guess you know already Emanuele very well. You can say how you were assisted him.
Yes,
there you is.
Again, Giuseppe, yes, let's say there is a long, let's say, friendship cooperation with SOITAB. So we are a distributor company. As OPTOPRIM Italy, basically we distribute Enlight for the beam shaping. So and what we did, we were just supporting also SOITAB, and we let's say understood how to better use the laser together with our end user. Because at the end of the day, we are just looking at the new frontier of lasers with the beam shaping. Is it something that has been announced a few years ago, but just recently has been used on real application? And so it's not easy today to say that this is the best setup we can use for cutting. And that's why Emanuele was just putting the questions, let's say the nozzle, the head, and a lot of other things are still, let's say, needs to be investigated for the next years. But I would say that if a company like the Marius company basically can give us the possibility to explore new frontier, we are all of us happy to work together. Because in any case, we are fighting against other technologies. So the photonics needs to be, or to take a better place into the metal manufacturing world. And this is our aim as a distributor.
Very good, Giuseppe. So, of course, we are here all to support photonics. And so we heard already so far, we are all on the right way. So very good. And Marius, of course, you see, you have a lot of options here they're offering. I mean, there are really many experts for this. And so hopefully we can also establish this connection. And then I would say we had for sure now upcoming an expert for laser heads. So why not focus on this and give the word to Markus from Presitech. Markus, you can share your screen when you're ready and the floor is yours.
Yes. Hello all together. I hope I can drag the attention for another 6 minutes to my presentation. I hope you see my slides. Yes, great. So it was a good choice from EPIC to take me as the last presenter, because I'm representing now in my presentation a lot of groups which have contributed to laser processing in shipbuilding industry with respect to joint R&D projects. And just one word to Presitech and to the previous presenter. So if you want to get the processing head, which stands 30 kilowatts for more than 40 millimeters of sheet thickness, then you should go and ask Presitech colleagues. We have the Pro Cutter 2, which is, I think, one of the most reliable cutting heads to stand really extreme high power. And we are also working together with K-Labs and working together with Enlight on improving the cut quality by using special beam shaping opportunities. But let's go to the presentation. So my presentation is showing some excerpts from different joint projects. Those who are from Germany here in the group, they know that German government is spending some money on bringing innovations into different areas. And photonics is one of the areas where German government is spending some money for some decades now. And one of the application fields where photonics may play a bigger role in the future is the shipbuilding industry. And what you see here are joint projects where Presitech was partner in. And I will slightly touch the results of these projects. And you see most of the projects consist of R&D institutes, of component providers like Presitech, from people who understand process and industry, and from the certification industry as well, and from the end users. So you see, we have here in that project, we had Meyerwerft and Blom und Voss. In that project here again, we had Lürsenwerft and Meyerwerft. So here in that project, we had Salzgitter, Mannesmann, and Siak, and Nordic Yards. So this is the composition of many of the joint projects. And so we are pretty sure if we start projects like this, that we really work in the area into the direction the end user wants the project to go. Let's start with one of the projects where Laser Centrum Hannover was one of the major partners. This was a project where we first time tried to bring hybrid welding for extreme thick sheet into shipyard industry. The idea was to have a one-sided solution, and you see that we combined the laser processing head with the scanner, with one-dimensional scanner, and two of the MUG torches, one in trailing, one in leading position, to be able to weld that thick sheet from one side. The idea also was to use possible sensor technology that day to do also direct process control or process monitoring. And you see the cross-jet, which we designed for the project, was extremely huge. Everybody will understand that that process is highly better correlated. And you see the results. So we had the results. We had to use a 16 kilowatt laser, arc power 2 times about 5.5 kilowatts. I think we pretty had a very fast process, and we had a slight joint preparation of a Y seam, but we were able to weld 20 millimeters directly one-sided. So, and actually, in comparison to other projects, we directly weld 1 meter length, because we have seen that just welding pieces of 20 or 30 millimeters always works. But if you want to show the results in nearly shipyard application dimensions, you need to weld a little bit longer sheet. Next was a project where we worked together with Fraunhofer IIPT and Fraunhofer IoT, and very important with the company Close, to bring 3D laser welding into innovative ship designs. So the idea was not only to weld in typical weld positions, so in all the weld positions which are happening in shipyards. So vertical, horizontal, going up, going down. That's why again we oscillated a little bit the laser beam with the robot, and we had a very high innovative seam finder. I will come to that later. But this innovative processing had guarantees good accessibility also under constraints, and this is important for Damen. We built a very, very impressive gantry system only for this project with 3 robots at the end of the gantries. That gantry system was built especially for shipyard applications, and this is now one of the bigger halls at the Fraunhofer IIPT. So we can weld very, very big parts, and as I said before, the demand always is to have sensors to directly control the process result. So the idea here, which was developed by Fraunhofer IoT, was a texture-based seam geometry and tracking and gap measurement system. We used the sensor technology to, with respect to measure process emissions, to directly tell something about the weld in situ. And we also had a seam geometry sensor based on laser triangulation to measure the resulting seam geometry based on the DIN EN 13919, which is a norm which is only for laser seams. And in the end, if you're not able to use robots, we also developed a very nice and compact handheld laser processing device, which is moving on its own. So there's a small a robot inside which is moving the head at a constant position. You see here a camera which is also looking into the process, and so the guy who is moving or who is taking care of that handheld machine can guide a little bit the robot and can take care of the process. So this is now a part of the Lürssen-Werft in Bremen. One of the more important things nowadays is in shipyard industry is to reduce the weight. And one of the possible ideas to reduce weight is to bring more aluminum into shipbuilding industry. And together with Laser Center Hannover, again, we were working together in a project where we tried to accurately join aluminum to steel. For everybody who knows welding of dissimilar materials, that this is a challenge. And it is even a challenge if you go to thick section applications. You see here that if you do not weld deep enough, you don't get any a joint between steel and aluminum. And if you go too deep, you will get brittle intermetallic phases. So that's why it is crucial to have a sensor which is able to detect the penetration depths. And for that, we implemented our well-known OCT device to measure and to control the penetration depth. That was combined with a Scansonic processing head in that project. And now we were able to directly control the penetration depths. For those who don't know the OCT device, so that is all based on fiber technology. Every electronics which are needed are in the cabinet, in the control cabinet. So everything you see which is mounted on the top of the welding head is without any electronics. And that especially is designed also for the industry, for industries like shipbuilding industry, where we have to stand very, very high demands of robustness. So just some messages for you to take away. Shipbuilding industry, as we see it, is continuously incorporating innovations, but it's a long and winding road, as I say, because even if the companies who take care of the norms are part of the projects, it really takes some years that new processes can be implemented in shipbuilding industry. Nevertheless, we have a high complexity of approaches, and as we see the contributions from relevant experts really bring that solutions very, very much more fast into the different applications. And we have been, and we are still, and we will be a reliable and curious partner for these solutions for welding, cutting, additive manufacturing, and for partnering in joint R&D projects.
Thank you very much, Markus. We love Presitec, and I would like to acknowledge VDA, PTJ, the Bundesministerium of Windkraft and Energy, and the one from Bildung and Forschung. Thank you very much, Markus, for a great presentation. Answer first the epic question. What can you do for the others when others can do for you? I want, like Francesca said before, the Santa Claus Christmas list of Presitec.
Yeah, so as we have now been partner of many of these projects, and we have seen that with our increasing application knowledge and increasing modules with respect to cutting and welding, we can build solutions very fast. So we don't start from zero when we join such projects, or if we work together with partners, we start from a certain level. And for those who do not know Precitech right now, they just can ask me or ask my
Who doesn't
colleagues.
know Precitech by now? Who doesn't love Precitech by now that you're collaborating with most of our members? It's really, truly great. Markus, before we go to the end of the meeting, which apologies for 30 minutes late, I would like to go to the end user again. I would like to go to Avio Aero because I really want to hear from them a bit of the takeaways as an end user from a meeting like this when we discuss so many technologies interesting for Avio Aero.
Yes, I think that for what we saw today, there are quite a bunch of items that could be very interesting also for us, because mainly as far as concern the laser drilling, all the application on shaped hulls, all the application that could lead to improve the performance of the engines, all these kind of argument and technology that would be really interesting for us. Everything that can be linked to that. Secondly, what we saw on the shot pinning also, we found it very interesting. And also the laser texturing has some margin of improvement and interest for our business. So let me say that at the end of the day, bottom line, the feedback of the day was very, very positive.
Oh my God, the end users telling us that we did a great job. Great job, Francesca. I'm just an entertainer. We have a question from Teraxion. Pascal, you have a question for Precitech. What's on your mind?
Yeah, in fact, I was wondering if having longer delivery cables would be beneficial for the naval, cutting or welding large pieces. Would that bring some benefits?
So we don't build fiber cables, but I know that most of the applications we have built solutions for, the standard cable lengths or cable length of 50 meters is not a huge problem right now.
Okay.
So the lasers, as you may guess, are not directly next to the line. They are typically placed in a room which is not facing -0 degrees Celsius.
This, in my opinion, has been a great meeting with a lot of opportunities for Teraxion and for many of the other EPIC members. Actually, I'm going to summarize here some of my rules for cooperation. We have from Prima Power, multi-beam solutions. We have from Thales, DOEs. We have from Damen, process monitoring. We have from Soitab, fiber lasers for the steel, multiple cutting solutions and optics and nozzle design. And Precitech was very happy about this. And we heard from Fraunhofer IAPT, we are looking for new laser sources. I've been shaping optics for additive manufacturing. We heard from all of you, and I summarize this in the slide. I really love this meeting, Francesca. Really, really great job today. Really great job for everyone. I live in Northwijk, next to the sea, and the government is saying today that the whole Christmas is going to be a lockdown. I don't mind, because I have 300 hours of footage that we have collected over the whole series of online technology meetings. If you want to get in touch with any of the participants of all the meetings, just send me an email, jose.pozo@epic-asset.com, and I will be more than happy to introduce you to all the participants. I love doing that. I'm not planning to rest during the Christmas. I just want to work. So ask me to make introductions. I also would like to let everybody know that we have already announced the season 3 of the EPIC Online Technology Meetings. All the topics are there. So on behalf of a great team of medical experts, identity photonic experts, Francesca on the laser, optics and quantum, the best innovation manager in the world, Antonio Raspa, marketing experts, Anna Faises, CFO, and the person behind the whole adventure, Carlos D. I just wanted to say, to repeat to you, this Christmas, stay home. It's very warm at home. Just wear a mask. Wash your hands all the time. Don't worry, you don't need to go to the bar or to the pub. Stay home and watch the footage that we collected on the 300 hours of online technology meetings. Until the next time, from Northwijk, the Netherlands, eating frikandel and drinking carne milk, Jose Porto. It was a pleasure. Bye-bye.